depth of the algebra for these orbital trajectories and the energy and momentum and all of that. Now I'd like to show a more elegant way to visualize the geometry of the orbits that we talked about. And we'll start off with a very direct application of the geometry to Rutherford scattering. We've already talked about this arrangement for a pair of hyperbolas of major radius A, minor radius B, but there's no necessity in hyperbola for having one bigger than the other. They can switch places very easily. But the idea is to get this thing connected to an actual scattering. So that's the first thing we'll talk about. And this will give us a chance to see some more of the envelope geometry that we worked on with the oscillator orbits, many trajectories, and then a contacting envelope. We have some really pretty simulations of that as well, and this one is no exception. Then this thing called the eccentricity vector. This is a symmetry object, and it's very much analogous to the Stokes vector, describing the two-dimensional coupled oscillator or polarization states. But this works for the orbits and is a little bit trickier, but also very beautiful. And then in having written papers about this and used it in classes, I discovered a parameter system that is much closer to the geometrical part of the orbit theory, and so we'll talk about that as well today. The connection formulas between these two is a little bit tricky, but it helps when you are dealing with orbits in an abstract way, but also for real cases of space flight and astrophysics. I think the most interesting Coulomb orbits are the ones that exist at the center of our galaxy, and apparently other galaxies too, that involve objects orbiting at enormous speeds because they're orbiting a black hole. And this stuff works pretty well for it. It's in a relativistic system, but there's some things here that make it go a long way and be able to handle some very high speeds. So we have some more animations that we'll see today, and some other things that are connected to this, plus American Journal of Physics papers that are of interest if you want to go further than what we'll be talking about today. So let's consider the Rutherford scattering thing carefully here. I'll get them on 3 screens at least. We'll have actually 4 screens to start with. But anyway, the actual construction that I want to demonstrate is on the 3rd screen there. And it starts just by assuming that we have a beam of, well, in this case, alpha particles, alpha plus 2, and it's the gold 79 nucleus that was being targeted by Rutherford, these experiments. And what you imagine to start with is a beam in which you have, say, equally spaced impact parameters. That's what the dashed lines are supposed to represent. And there's this particular a trajectory that we're going to calculate, just a ruler and compass derivation, has at a great distance, a certain distance to above, lying above the line that goes dead center. So the gold nucleus is sitting here at this focal point. This is an empty focus. There's nothing there, but mathematical significance of this is just as important as that one. So the main focus has a gold nucleus sitting, and then alphas are coming in horizontally and experiencing the Coulomb field of this object and deviating away from it. Now the construction we won't spend any time on this time, but it's something that is quite equivalent, and that is if the alpha particle were a negative charge and was attracted to the nucleus, the conjugate trajectory right here that bends around it feels its attraction and continues out. A scattering that occurs for it is in many ways identical to the one that we'll get for the repulsive case. So that's another topic that we'll bring up in the last few lectures of the class. So anyway, remember the formula that I told you never to forget for Coulomb energy. The K over 2A. That marvelous energy, total energy, that is only a function of the parameter A, not the B. Only the major axis is important. This is true whether it's repulsive or attractive, whether it's hyperbolas or ellipses or circles or parabolas. So in this case, the dead-on closest approach is what we're imagining here. We're imagining that lucky alpha particle that gets the biggest push by bringing it to a complete stop. And then it just turns around and skedaddles out of there at the same rate that it came in. So once you know that that happened, then you know right away that 2A is the distance that it got to. And that's what this formula is telling you. So all of these things have a certain energy E. No matter what that energy is, and whatever the constant, it depends on the charges and all of that. But we're imagining that it gets a certain distance away, and that distance is twice what we call the semi-major parameter, axis parameter. Okay? So then it's just a question of taking this picture and realizing that for all the other orbits, to be the same circle, we're just going to lift it up or push it down by a certain amount. And that's what the construction on the third screen there is doing. So see if there's anything else I need to mention here. Well, one of the things I want to mention is that Rutherford never really got the alpha particles to impinge on the actual nuclear structure. Well, some people would say he didn't even come close, but he still got to within very small distance, and that much smaller than anyone I could think. Now, I also should mention that these alpha particles in these pictures that we're drawing here are already inside the electron shells for the gold atom, well inside there, up in Springdale and down in South Fayetteville, compared to this picture that we have here. So there's a long distance where the alpha particle basically is traveling through just a very weak electronic wave function. And electrons are 2,000 times lighter than a single nucleon, and this is an alpha with 4, so we're not even considering that at all, and that did not register on any of the experiments that Rutherford did. So it's a clean problem. It's a very clean piece of physics that's going on here. So let's get this on all screens here so we can talk about it. The basic idea is that if you want to find out what's going to happen to the alpha particle that's on impact parameter B equal a unit, or any of the higher ones, well, it's just a matter of drawing a circle at the radius A away from the vertical. And then the next step is to just copy the angle between the line, draw this line, and then copy that angle to there. And bingo, you found this direction this thing is going to scatter out on. It's that simple. Is that more or less clear? So this tipped over alpha pattern that we're looking at is tipped over for this particular scattering by exactly that amount. Okay. So this is one of the kinds of angles that, this is the forward scattering. How much forward are you in your scattering? And I would call this the backward scattering angle there. So at this point, if that's all you want is scattering angle, well, that's how you get it for a particular impact parameter. So the next step is to find the focus, the other focus, the one that has nothing sitting around it, and get all of these up to that point. Here, all I have to do is, after I've drawn this line right here, put a compass there and strike an arc over to this line. So we know the two foci are balanced around the center of the orbit. And then the next step is, which we'll draw pictures of it, just to make everybody in the class go ahead and construct from these two foci the actual hyperbolic points, say a dozen of them, and that's what we'll show pictures of in just a minute here. So that's basically it. In the backward scattering angle right here divided by 2, it is that's this angle right here. Is this angle has this as its right triangle. So that is what we're dealing with here. Now, half angle is complementary. Full angle, supplementary, or whatever you call it, 180 degree difference, pi difference. Okay, so using these two focal points and imagining a string going to the actual point that the orbit is, that's the more tedious part of any of these constructions that we'll be talking about today. But just getting the basic geometry first really is helpful. So let's look at it a slightly bigger picture here, and go with the actual construction. And there's the beginning of it right there. But the basic idea, as I say, is either the back scattering or the forward scattering, whichever you want, but this one is easier to envision for low impact parameter, and the other one is easier to visualize for high impact parameter. And see if there's anything. The other thing is that there is a focus locus to this hocus pocus. This line right here is where all the foci will be parallel and 2A far away from the beam face, the line perpendicular to the beam direction, just above the actual gold nucleus, which is there. So all of the foci are on that line for all of the different impact parameters, either scattering up or scattering down. So that is kind of neat, and that's what we're looking for in all of the more complicated constructions that we're going to be doing. So the actual procedure for calculating the orbit is just take the compass and strike an arc. Anything bigger than 2A is fair game, and just happen to pick that one right there. And then be aware that the distance r prime to an actual orbit point for a hyperbola that we're talking about here, the difference between r, the distance to the prime focus, or the original focus, and then the empty focus, the second focus. Okay, this is r, and this is r prime. The difference between those two lengths is just 2a. That's this distance right here. So you figure out where this thing hits, and then you simply subtract the r prime from that, and you measure that distance, r minus r prime, take that, whatever that distance is, let's see if I've got this right here. Actually what you do is you use the r that you picked, and then you find out what r prime is, and you take the compass and set it to that, and put it on this focus, and strike an r. You get 2 points for the hyperbola. Then you just do it again with a slightly bigger r, get a slightly bigger r prime by the subtraction down there, and strike that arc off, and then do it again, and you know, pretty soon you have a pretty good idea. This is just a half a dozen or so points, and then the same number up there. A pretty good look at what the alpha particle is actually doing, and it's pretty amazing that it is already this high above its original beam direction that it would have had if the nucleus wasn't there. It's already that high, and then, bingo, it's going to be going up, and symmetry around this axis makes this reflection of that. So there's a typical orbit constructed, just ruler and compass, we take it. No algebra to speak of, except for that k over 2a energy. That pretty well settles this. I should have been following along here. Just look at it again. That's the drawing, and then that's the trigonometry that goes with it, which we're going to be using to get the cross-section, the differential scattering cross-section for this. So, okay, now that's pretty easy. There's the right triangle, gives those two scattering angles. Just take your pick. And well, that's that formula is what we really need in order to get them. Now let's let the computer do the job. That's why you're not sitting here now like in the old days that I taught this course, working a ruler and compass on some graph paper. I will ask you to do one such construction for the next problems, and it's a good way to remember how this works. But anyway, this is this comes out of a program I wrote quite a long time ago called Cool-It, and TC has really made it a much better. This is the old crummy program right here, but now we can make much nicer orbits, and all of these orbits have a beautiful envelope. Okay, that is little, very analogous to the envelopes that we made with the volcanoes of Io, or in the very small atomic laboratory, the cesium atoms that make a little fountain that we use for and that the National Institute of Standards uses to keep our time. The difference, of course, is that the parabola that was the outside of the fountain, this has got empty space where that was. This is now sort of the flip of that. This is the alpha repelling all of these orbits, making this perfect. Well, it turns out it's a parabola. We'll see that we can prove that fairly easily. So, what I'd like to do probably is turn on this one, and I'll probably do it best on this computer. This is a little faster than this one, even though it's older. And I'll take this one down to that point as well, so you can see what it is we should be getting if this works. So let's go ahead here now. Several points in this lecture, there are pages that show the control panel for Cool-It, but we do a lot more than just this particular scattering event. And also, before I go on, let me emphasize that when we're thinking of the alpha thing, it's something happening in a tiny little space. Here's something that's happening as we ride on our little Earth around the sun. and both of us travel around the galaxy, around the Milky Way. And what's amazing is that this is an approximate model, and it's a pretty good approximation for deep space H-atom scattering from the solar wind. So there are a bunch of hydrogen atoms. Everyone knows this is the case because 21 centimeter spectroscopy tells us that the universe is filled with hydrogen. It's not very dense, but you take enormous volumes and it begins to make an observable phenomena. And for each spectral part of the hydrogen, Lyman alpha is this particular one that I'm thinking of, because that was what my friend Darrell Judge discovered as the Mariner Mars Mariner not satellite, but space exploring device, one of the first to make it into the vicinity of Mars, crossed the bow wave of our sun, the Lima alpha bow wave. There are a lot of others, but this one is really pronounced. And it's about 1.2 astronomical units from the sun being right there. So we're sitting on Earth right here, we're sitting in a spacecraft, and it crosses this thing. That's amazing. And not only that, but it pretty much has this shape. That's something that hasn't been measured very far, and basically been measured in this area, but we've seen it on other situations. So we know it's something that's a pretty good approximation. Now you remember, the solar wind consists not just of light, but of quite a number of particles that make a more substantial wind. But we are just talking about light here, the photons at the frequencies that involve Lyman alpha, UV radiation. And the electric field vector, the radiation goes inversely with distance, but the intensity, the thing that really counts, goes as inverse squared. So there's a repulsive Coulomb force coming from the sun, and this is experiencing it, making the envelope. Okay, so that's another application of this thing in the large as compared to the alpha scattering business. Anyway, enough talk. Let's run this scattering here and see if it can get it started here. I should have tested this darn thing before. I'm always having trouble with this guy right here. That seems to be the right website. Let me go back, see if I can pick this thing up. Okay.
Kill Firefox and start afresh. I have no idea what state that's in.
Oh boy, I didn't have any trouble with this when I tried it this morning.
Yeah, I tried it too. We double triple checked, but
Yeah,
not here with the wireless.
that's,
Signalless is what they should call it.
yeah, something weird's going on here.
If you quit the app altogether.
Force quit.
Yeah, it just might be
Firefox.
hung. See, it's hung. Not
Yeah.
responding. So the next launch ought to get it. She got bars.
Okay. And I'm set to pick up Firefox when I do it again, but let's see what happens. Go here. 2. This thing's covering it, so I can't see what I'm getting. Let's go back and see if I can pick it up by starting it.
I was installing an update.
Oh,
I think that hosed us a week ago too.
Here we go. So here comes the, and we're assuming, we're just looking at the set of alpha particles that's started here. They're still pretty much in line with where they would have been at basically many angstroms away. But you can see only about now as they start to bend a little bit, and the one that's dead on is still moving toward the gold nucleus, if you're thinking of that experiment, Rutherford, and now it's stopped. and now it starts to go back. But the others are doing other things. And there it is. That's the formation. And then there's sort of a little contact region right there that are contacting this thing. There's a parabola. And that's the movie, okay? And of course, if you want to resume, it's set to stop at a particular place, you can let it go and make the whole parabola, and they all go off the screen. There's the thing. Now, what's going on also here, in this, we're now imagining the quantum mechanical situation. TC has made the program so that you can plot the action, just picking up, particular units, but the colors here represent the actual quantum wave that would be associated with the wave function for this whole scattering event. And the only thing that's missing, of course, is the amplitude of that wave. The frequency wave number is given by the colors, but this ridge here could have an evanescent lip, that is an exponential lip, a little bit off the side. Aside from that, that is the basic wave function structure gotten with classical mechanics, and we talked about this back at the end of Unit 1, Chapter 12. So that's this picture right here. Now, one of the things that you notice, if you strike a compass, and from here it doesn't fit very well at this point. Bring it over a little bit. There's pretty close to a circle center. This circle, you can see it works very well for that point, but then it starts to get outside of these points here, and then get inside of them here. So obviously this isn't part of a very good circle, but it gets better and better as you get closer and closer to here. And then this is the interesting thing that we'll talk about next chapter, sort of, is that this center creeps, just keeps creeping closer and closer. For this particular scattering event, those alpha eventually are on a circle going away from this point, even though they've had to go through this elaborate dance to get to that state. So, there's a lot to be seen by, this is just stuff that you don't find in mechanics books. They should be in there, now that we have computers to make us see that, but that's the way it goes. Anyway, the number that this is 221 of the suckers. Obviously, with a faster computer, you can use more and just smear the thing, but this is certainly enough to see what it is we're getting. Okay, now the analysis of the geometry for this is, since we've talked about the kites of a parabola, the kite plays a role here. And this came long after I'd written the paper on that, and we still haven't published anything about this little structure that I'm going to show you here. But remember that the second focus is on this focus locus right here, second focus locus. Okay, and at this particular juncture, we've picked an impact parameter that's right here, and we just draw a line through there till it's above the center, and that's where you make the next asymptote. This is the forward scattering angle right there. Then there's the asymptote that this trajectory, the green trajectory, is going to be approaching, having left this asymptote. So the incoming asymptote has the stuff that we showed. It slowly rises above the thing. There's the closest approach to the nucleus, okay? And then it's going to come back as we go way out there. Finally, we'll lay back down again on this asymptote line. But what we're interested in is where it makes contact with the envelope. Now, I've drawn the envelope in here, but how do you find that envelope? You see, and that's the curious thing about this, is that what you do is you go up here and you look at this particular point here, and you see where the center of that is, and you make, and I'm more interested in how that line right there intersects at that particular point. I draw a kite turned up. This is the front top of the kite right there. The yellow is the bottom of the kite. And remember the kite, the parabolic kite that finds a tangent on a parabola. There's the center of the kite making the tangent, and this little point here indicates exactly what the slope of that tangent is. Well, the same thing's happening here, except it's sort of cattywampus with respect to the that picture. And once you've found this thing where it intersects, and then have a certain point associated with a line from here to there, that's just double this, and you then can construct the line that's the center of the cut, and that will be the tangent that's hitting this particular envelope. There's the contact point. And remember that contact point is being played off of this focus here, as well as the second focus. This is a parabola though, so its focus is at infinity. The envelope parabola's focus is, there's only one of them, the other one's gone. But then this is the other focus right here, it has to be in line with that one at infinity. And so you then finish this construction in just by having that particular point there. So you can see the parabola right there just seems that thing, and then the envelope continues and curves over to make the other points, turning points, you might say, of the caustic, I guess that's the name for the envelope that's maybe appropriate here. Okay, so that's, I think, neat way to look at the gears behind all those orbits and making of that envelope there. This is just a better picture of it. A sketch. The actual construction on graph paper is here, where you can see this is a B=3 hyperbola contacting a little bit lower on the envelope. So the red thing is the envelope, and then this is the actual, that particular alpha particle that was contacting there, then continues out here and eventually gets to the asymptote, up a few yards to the left and up. Okay, so at this point you check to see if your geometry is working out, and we get about 2-figure accuracy, maybe one figure to be ungenerous, but that's the actual scattering angle that is coming for this particular orbit right here that has 3 units of impact per amplitude. Okay. All right. Now remember, the kites there was a square kite, and then there was the sort of the Asian kite that was very symmetric. That's when you go inside the focus of the parabola. Well, I got an example of first the square kite right here. This occurs right here when you have the B equal to 2A. If your impact parameter is equal to the major diameter of the hyperbola, that's when you get a square kite, and the contact point sitting right there. The weird case is when you go inside the focus, make the impact parameter less than that, really heavy scattering, then you get an Asian kite. In this particular case, there's the contact point right there. Okay, so this kind of makes it possible to visualize things that I don't think have been seen before. Okay, let's see if anything else I have to say. The scattering geometry, but we're interested in, or if you're Rutherford, you're interested in how much of the stuff you're getting at a particular angle. You're interested in differential scattering cross-section, and that is basically mapping this little input window right here, differential of the impact parameter, some small distance, and everything that goes through this window here has to come out in this thing right here. Now that, of course, is not pointed at the origin. Remember, these the points that these loci move in, and this is another one that starts out here someplace and eventually moves into this point. So your actual scattering will intersect with this one. This one is going to close in on that, and that angle right there, the differential scattering angle, will eventually meet. But in the meantime, all we're going to do is count. Everything comes in here has to come out there, so we're going to figure out what happens as something that comes in from x equal minus infinity and then goes out to r equal infinity. We're talking about an area that is just the polar metric, sine theta, d theta, d phi, and phi we can pretty well drop out fairly quickly here. So this is the incremental solid angle into which that will scatter. And the ratio of these two, d sigma to d omega, that's a derivative. It's an actual derivative of b with respect to theta, is what comes up here. This has to have symmetry in order to work. So the azimuthal angle, this angle around the beam, is dropping out. So it's this thing, and by geometry, this b over a is cotangent. Turn that derivative, the db d theta, is then cosecant squared. So we have to put that in. That's, of course, inverse sine squared. And that has to be equal to, this is the formula to never forget, k over 2e is the a, that is, the energy is k over 2a, so the a is k over 2e, and putting all of that together gives us a formula which is very simple. It's the fourth power, inverse fourth power of the scattering angle is the amount of stuff coming out per solid angle after scattering at infinity. That's what you're seeing in that tube right there. So all this stuff cancels to that, and that's kind of neat. Now what's neat about this also is that this classical result agrees with the quantum mechanical one that's usually used in describing Uffe-Furcade, and it's called the firstborn approximation. So it isn't the most accurate thing that you could possibly have. There's second and third and fourth approximations give very small changes to scattering the energies we're talking about here. But this is an interesting case where classical mechanics gives a quantum mechanical result quite closely. Okay, just for the fun of it, I want to make a contrast between the total scattering cross-section of this thing. This thing that has a sine to the fourth here, you know right away you're in trouble with this. This is going to blow up. Okay, trying to figure out how much of the beam actually got eaten by this Coulomb field, and it's all of it, basically. That's the conclusion that arrives from this. Now, if you do something like this, and I will go ahead here, get this thing back into the slide mode, and go ahead and run the animation for this particular case, just to make the point that differential scattering cross-section has a total cross-section for some things. Most simply is this one right here, which we call hard sphere scattering. So here come those alphas, and now there's some kind of weird potential there. It's absolutely hard, bounces them off, and off they go in a circle. It's not quite centered, but when you get very far away, it'll look like it is. But the total cross-section for this is exactly that, the area subtended by that sphere. And that's something that's interesting to do. If you want to try these formulas out for this, it turns out to be pi r, where r is the radius of that ball. So that's what you get for the total cross-section, and that's what you should get. It's just eating that much of the beam. But that's the thing about the Coulomb. Infinite. This just keeps working, right? And it's the best way to see that I can think of. Okay? All right. Let's see if there's anything else. I think we're ready to do the general case. This is very nice for something that starts at infinity. The alpha beams start very far away from the scattering center, and that's what made that geometry really simple. But the next thing is simple too, but I would say much more powerful in the sense that we are doing a general case. All possible Coulomb orbits are being tackled now. We're going to get a geometrical construction that works for everything that's Coulombic. Okay, and it involves this weird vector called a lens vector usually, but it's got more names than that. It's actually the Laplace-Hamilton-Gibbs-Runge lens vector, and maybe some more. I mean, after a while, you name gets down to here. Maybe I'd stick mine on for the little tiny contributions that I've given to the geometry of this thing. Okay, but this guy's always got his name in practically everything. That guy's pretty smart too. Here's the American that helped or independently discovered this. So what I'm doing for the sake of comparison, remember these two potentials, the 1 over r and the r squared, those have this higher symmetry that allows us to play games with vectors that describe conserved vectors. Besides angular momentum, these are all isotropic potentials, but these are isotropic in some kind of higher dimension. What higher dimension? Well, some of this will be discussed in the group theory class that I hope to give in the spring. But this one is actually an orthogonal group in 4 dimensions. This is a generalized 4-dimensional sphere, which is an outer product to 3-dimensional spheres in a weird kind of a beautiful way. And then this one is very obviously the unitary group of, well, 2, if we're talking about a spin half, but this can be generalized as well. So this is just for the sake of comparison of what this thing, this magical vector with 5 names is going to be giving us. And it's not the way it's stated. It's usually stated without the constant there. They put it on this thing, and they call it A. But what it is it's the eccentricity. So it should be called the eccentricity vector. You won't, if you look up eccentricity vector, you won't get this. But if you look this up, you'll see it, and it won't be stated quite that way. But this is the way it makes sense geometrically. If you want to do ruler and compass constructions, this is your baby. Okay, so that's what we need to describe here. And here's the proof of it. Here's what shows that given what we did the other day, which was build an orbit equation out of R, this thing gives you that equation by simply considering the dot product of it with the radius vector. So there's epsilon dot r. Now I found it amusing to also consider the dot product with momentum. So remember what we're doing here is working with a vector that is conserved. We know L is conserved, angular momentum, that's conserved by any isotropic potential. But this very special O4 potential is conserving this crazy thing. So, dot it with R, dot it with P, you'll get something that, if you're lucky, makes some sense. Okay. Now, I'm going to skip over most of the things that we do with this, but it will be part of the story. This is the one that you should probably look at, and that's the one we're going to construct mostly today. Now what I want to do is let there be an angle between wherever this vector is and the actual radial vector. This thing's standing still, the r is on its orbit, whatever elliptical or hyperbolic orbit it makes. It's going to be having a variable epsilon dot r, but I can write it as cosine, that's the dot product, and then while I'm at it, I can switch the dot and the cross here, so I get r cross p dot L. R cross p is L, so this is L dot L, that's L squared, that's a constant. So this particular term right here is a constant. This is the thing that's going to be variable, and so is this variable because it's got an r on it. P moves as well. This is the thing we have to finish. That'll be our pièce de résistance today. Anyway, there are the components of our hopefully intelligent geometry. And you can see right away from looking at that center screen, that's how it matches. Just writing the dot product of epsilon with r and letting it be adjusted, the algebra adjusted a little bit, I can get you r equal L squared over km divided by 1 minus epsilon cosine. Sound familiar? That's the equation of a general conic. Remember the one that we used as the epsilon, okay? So that's why I call this the epsilon vector. It is the epsilon that is the eccentricity in the general conic. Jackpot. So, just to check it out, okay, for phi equals 0, you're talking about an apogee. That's the thing that's off the screen there, the high point, apogee. And then pi over 2, right here. That's our lattice radius, no longer called lattice rectum. Don't forget about that. And then with a larger number, 1 plus epsilon, and you got a smaller number, that's the perihelion distance there, and perigee being the low point in the orbit. Okay, if it's an elliptical orbit. But the thing is that this is going to apply to all of the conic orbits, attractive or repulsive, all of them. It's taking care of the whole schmeal. And that's what's so really powerful about it as far as classical geometry goes. If you're talking about an attractive, and remember when k is greater than 0 by our convention, that's attractive because we write the potential as minus k over r. And then when we make it repulsive, which I'll put right here, let's get these things all on the screen now. There are the three cases that our orbits can be, okay? Only one of them is elliptic, but it's a pretty large case, and we're living on an elliptic orbit of the Earth around the Sun, and then the Sun and Earth around the galaxy, and so forth. The energy here is less than 0. And then the other attractive orbit is when you crank that energy above 0, you get a hyperbolic orbit. And then, forget those two, let's take a repulsive Coulomb, the Rutherford case, where we're scattering things that repel each other. The energy there are always greater than 0. We don't have an energy less than 0 case for this repulsive Coulombic field. Let's go back to the graph here and connect with the eccentricity formula right here. Here I've got the momentum going this way. I've got the angular momentum right-hand rule. The L vector is out of the screen. Say, if you want that to be your origin, which would make sense, that's where the scattering would be about. And this then would be P cross L with a minus sign there to give us this vector. And you see, that's the idea. Epsilon plus that vector, epsilon plus that vector would give me the radial vector. Okay, so there's the radius, there's the P cross L, and there's the epsilon vector. The eccentricity is represented by a vector that measures how eccentric the orbit is. And if it's a circle, that shrinks to 0. And we're back to doing sophomore physics. But all of the rest of the cases, including this one, this is quite neat. If I crank the energy up, then this attractive orbit is attracted by that force, but it's got so much speed that it's get straightened out. And in fact, if you make it really fast, it's just a straight line. It doesn't even have a visible bend in it. But nevertheless, it will still be treated by this same sum formula right here. So there's the minus P cross L, and the sum of that and that gives you your radius vector at all times. And then there's this weird guy, okay, the Rutherford case, okay, repelling. In this case, this is a nothing burger. The second focus is nothing there. The actual attractive, I should say repulsive, force field center is right there. And then this is an attractive force center, and this is too. This is the nothing burger sitting inside the orbit, and there's the nothing burger focus sitting outside. Okay, so those are all the cases, and that's what we needed to before we're done with the lecture here today. Okay. All right. Just to remind you what we had to go through in the last lecture, and the results are being stated here. The table of physics versus geometry is pretty much the same as the one I gave you. I added this little piece there just to help. So what I wanted to do now is talk a little bit about the geometry that has to do with the P dot R, but I'm not going to do much with that. It is a kind of a neat thing. It says the projection PR of the momentum onto the radius. It's the R or R prime radii. Either the radius that actually comes from the force center or the radius that comes from the nothing burger focus. That has to be epsilon times the projection px onto the x-axis, the axis that has the eccentricity vector, the unit eccentricity vector. Okay, so that's kind of a neat thing that we can use for some stuff. It's kind of hidden in what we're about to do. This particular graph is not taking into account the fact that the P is going to get big as we go to the thing. That'll become obvious later on. That's the, it falls, it gets faster as it falls towards the center. At this point, that thing makes the